Second morning session. Our first speaker is Vicente Rudiger Gomez, and he's going to talk about optical morphologies of galaxies in IllustrisTNG.
Okay, thank you very much. Can you hear me? Is this working? I guess I have no pointer. Oh, anyway, yeah. So, hi, my name is Vicente Rodriguez Gomez. I am currently a postdoc at Johns Hopkins University, working with Jennifer Lott. Although I will be, oh, yes, thank you, thanks. Yeah, currently at Johns Hopkins, I will be starting a faculty position at the UNAM Institute for Radio Astronomy and Astrophysics in a couple of months, so that's where you can find me in the future. And, well, today I will tell you about some ongoing work with the IllustrisTNG simulation about measuring their optical morphologies and trying to make oh, you cannot hear me? Okay, is this better? Okay, so the idea is to make okay, yeah, so the idea is to make an apples-to-apples comparison to observations. So, yeah, should be straightforward. Well, so as we'll know, the morphology of a galaxy is one of its primary properties. Correlates with many other with color, star formation, gas fraction, environment, sizes, etc. And it's interesting that at a fixed stellar mass there is a great diversity. So, yeah, this is just a pretty picture I found online. Now. Well, so of course, any complete galaxy formation models should be able to predict the correct mix of morphologies. So in recent years, hydrodynamic simulations have made enormous progress in doing this. This is from the Illustris simulation, and you can see that it produces it does a reasonable job of producing a mix of morphologies. So you have some ellipticals here, disks, irregulars. So just to clarify some of the terms, I refer to optical morphologies to anything that is obtained from an image, and kinematic morphology is something that all theorists like to do because it's easier. It's just you just measure like the fraction of stellar particles in circular orbits. That's easy to do, but it's harder to do in observation. So, for example, the Kappa Parameter, defined by Laura Sales, measures the fraction of kinetic energy invested in order rotation in a galaxy. So that's what is shown here as a function of mass. So you can see that galaxies around Milky Way-sized galaxies are the most disking. And this does a reasonable job of distinguishing disks from ellipticals, just using this parameter. So one of the things I did with Illustris was to see what physical properties drive are responsible for shaping galaxies. So two of the most obvious candidates are, of course, mergers and the spin of the dark matter halo. So the idea is that disks are more likely to form in fast rotating halos with not many mergers, and spheroids would form in slowly rotating halos that have more mergers. So it's a very simple idea. So here, so in order to encapsulate the importance of mergers into a single number, I'm using the ex-situ stellar mass fraction, which is the x-axis here, and the y-axis is this Kappa parameter that measures morphology. And the different panels are different masses, so low, medium, massive. So we did find a correlation, but only at the most massive galaxies, and the situation is less clear at lower masses. So even for galaxies that have mergers at low masses, they don't necessarily turn into a spheroid. Then we did the same with the halo spin, and we found the opposite, that actually a halo spin seems to matter more at low masses, and that at higher masses, the effect of the spin seems to be erased by other effects like mergers, etc. Here I try to encapsulate everything into a single plot. I mean, it's a lot to digest, but this is basically the illustrious prediction of what shapes morphology in a single plot. So here the x-axis is the halo spin parameter, the y-axis is the ex-situ stellar mass fraction. Different panels are stellar masses, and the color is the morphology measured by this Kappa parameter. So the idea here is that if the color gradient is horizontal, as here, then halo spin is what matters, and if the color gradient is vertical, then the excitostellar mass fraction or mergers are the most important. So, sorry, this is all at redshift 0. Yes, yeah. Although we did match it to a dark matter only simulation just to make sure that the galaxy itself is not affecting. So anyway, so this is all great, but these are kinematic morphologies, and I'm here. I mean, it's not easy to measure these. I mean, with IFU surveys you can approximate it, but still you don't have the 3D information. So, so now, I mean, the next stage is to measure optical morphology, something you can measure from images. This has a lot of information. So there are at least 4 ways to classify optical morphologies. There is human classification, like the Hubble sequence, and this includes recent efforts like Galaxy Zoo and Citizen Science. There's parametric, such as stereoscopic profiles. Non-parametric, like concentration, asymmetry. So the idea is that you don't have to do any kind of fitting, so that's an advantage. And I would say that deep learning is like, at least in terms of technique, is a completely different thing. So this is like the kind of stuff that Mark Huertas and others are doing. But for now, however, I'm not planning to revolutionize how we measure morphology, so I will just focus on these two, parametric and non-parametric, and try to compare the simulations to observations. So very briefly, the observational survey that we try to mimic is from Pan-STARRS. In particular, it's called POGS, the Pan-STARRS Optical Galaxy Survey. Has around 60,000 galaxies. However, I constrain the sample a little bit, so I get a subsample that is only around redshift 0.05 and less massive than 10 to 11 solar masses or so, just to make just so that it's complete and I can make a direct comparison to a single snapshot from Illustris. Yeah, so I'm sacrificing a bit of statistical power, but like here I'm showing the stereoscopic index n versus stellar mass. I mean, as you know, disks have a stereoscopic index of 1, which is an exponential profile, while ellipticals are closer to 4, is the Baculor's profile. So I'm sacrificing a bit of statistical power, but this is just for the sake of having a cleaner comparison to simulations. And this is the same. This is the Genie M20 diagram for those of you who know what this is. But, same, it's also a bit degraded. So the synthetic images are being made with the SCIRT radiated transfer code. I've heard a lot about Sunrise this week. Yeah, Sunrise is great, but SCIRT is also great. I recently started using it. It has the nice feature that you can actually do the radiated transfer directly on a Voronoi mesh. So I think this is particularly well suited for simulations run with the Arepo moving mesh code. So this is showing just a dust torus at different resolutions. Yeah, I won't go into the details of the dust attenuation and scattering, but you can ask me. So okay, so let's look at some images. This is an example of an idealized image. Idealized means that I have not convolved with a PSA to mimic the telescope optics, atmospheric conditions, or added background noise. So this is like the direct result from the simulation. The one on the left is not including any dust modeling, so the galaxy is basically transparent. Then the next one, this has the full dust modeling. And here I'm decomposing just the light rays into the direct, the ones that are directly coming from stars but attenuated, and the ones that are scattered by the dust. So you can see, I mean, there's like maybe you can see a dust lane or something, so it looks okay. And this is an example of face-on a galaxy. You might notice, I mean, maybe it's not so easy to see, but you might notice that it becomes a bit less concentrated near the center once you add the dust modeling. And this has a measurable effect on the morphologies. Okay, so here's another example. You can also see it becomes less concentrated and maybe some dust lanes. And the next step is to add, to convolve this with a PSF that is similar to the Pan-STARRS PSF, and to add some background noise, and then to do the morphological measurements. So we actually developed a new code to do the morphology measurements. It's mostly based on Jennifer Lott's ideal code to measure Genie, M20, etc. But I try to make it a bit more like user-friendly into a Python package that you can just download and run. So yeah, I don't have time to explain everything, but it does, the usual Genie M20 concentration, asymmetry, etc. And also Sersic fits. Although originally we only cared about non-parametric morphologies, I also included Sersic fits just because of their popularity. But it's a single component Sersic fit. I'm not trying to compete with Gal fit or anything. It's just for comparison. And the code is, we decided to make the code publicly available. You can find it there. It has like tutorial, documentation, etc. Okay, so now I will show you some results. This is all preliminary. But okay, so we have here we have okay, so first of all, if you're going to do some dust modeling to check the sanity of your dust model, you look at the colors, I guess. So this is without dust. You have pan stars here. This is a G-I pan stars band versus stellar mass. So you can see the bimodality is not too visible here, but you can see like the red cloud here and the blue cloud. In IllustrisTNG, if you don't include dust, it's doing an okay job, but maybe the bimodality is a bit too strong, and in the Illustris original, it's also too strong, and the red cloud is underpopulated. Once you add the dust, you can see that basically the star-forming galaxies move up, and you actually get I think a much better agreement. And I'm gonna say that I did not tune this in any way. I just included a dust model that I considered reasonable, and yeah, thankfully this happened because it was a lot of CPU hours. So now this is the Sersic index. We have the pan stars on the left, and IllustrisTNG Illustris with no dust. So for example, you can see that at low masses, maybe the Sersic indices of TNG are a bit too high, because you should get n equals 1 at low masses. Here you're a bit higher than that. This is without the dust. Once you add the dust, you get a decrease. So the galaxies become less concentrated here. And same in Illustris, but Illustris is producing way too many of these galaxies. This is the Genie M20 diagram. You have a similar situation. So there's no dust. So galaxies move a little bit lower to lower Genie and higher in 20. And then if you measure a quantity along the main locus of the Genie M20 diagram, something we call the Genie M20 bulge statistic, then you get this, and it's very similar to the Sersic index. And you find the same behavior. Once you add the dust, then galaxies become a bit less concentrated at low masses. And finally, this is a plot of the concentration asymmetry, other famous non-parametric morphology measures. And when you add the dust, you can see that in general galaxies move a little bit towards smaller concentrations and higher asymmetry in both Illustris and TNG. So this is actually a superposition of like a red galaxies and star-forming galaxies. So anyway, so my conclusions are that kinematic morphologies are, we investigated this with Illustris, and we found that they are mostly determined by mergers at high masses and by halo spin at low masses. However, if we want to measure optical morphologies, then we created a bunch of synthetic images with skirt for both Illustris and IllustrisTNG. A nice feature of skirt is that it can do the computation on the Voronoi mesh, because then you have the correct dust density everywhere, or at least consistent with the simulations. And dust model, the dust actually has a measurable effect on the morphology, so it makes them less concentrated and asymmetric. This is expected, but it's nice to see in a cosmological simulation. And yeah, the morphologies of TNG galaxies are in broad agreement with observations of pan stars. Pan stars, by the way, is a bit deeper than SDSS, so it's better for morphologies, and they are in much better agreement with observations than the original Illustris. So thank you very much.
So I could see from your first or second image that Illustris is producing bars, but do you have any sense of what the bar fraction is, or if people have looked at that? It's a side question from your talk, but.
Okay. I have not looked at bars at all. So
Okay.
That's a future work.
So I think the matches to the star-forming galaxies are pretty impressive, but I was paying special attention to red sequence galaxies, and there seems to be a big problem there. And let me state it, see if you agree. Cercic indices are not high. And so I'm wondering what is the structure of those quenched galaxies?
So apparently we are. I mean, the galaxies in illustrious and in TNG as well are a bit too disky. We are underproducing the ellipticals. So the problem there is that the dust. I mean, the dust mostly affects the star-forming galaxies. So there's not much that I can do with the more massive ones.
I was really hoping that TNG would be able to tell us how these galaxies were developing their envelopes and so on, and now I'm really wondering.
Well, no, I mean, you can. I mean, it's an improvement with respect to illustrious, and for the elliptical galaxies that you do create, then you can say many things. The problem is that maybe they are not as numerous as in observation. Anyway, this is a very strict test of simulations because it's based on the images.
More question? Okay, so let's thank Vincent again.
Okay. Thank you.
Our next speaker.